Hello and welcome back to Vector Flow. In today's video, we are going to talk about the history of neural networks. All of modern AI, so ChatGPT, image recognition, and even speech recognition, traces back to a single paper from 1943. 8 decades of ideas, setbacks, and breakthroughs compressed into one chain of thought. This video covers the whole arc, the math, the people, and the exact moment each idea changed everything. So, let's start with 1943, where Warren McCullough was a neuroscientist and Walter Pitts was a 17-year-old math prodigy that he met at a library. And together, in 1943, they asked, can we write an equation that acts like a biological neuron? This neuron fires when its input signal crosses a certain threshold. So, they formalized this. The output is 1 if the weighted sum of inputs is greater or equal than theta, and 0 in all the other cases. That's the Heaviside step function applied to a dot product. Simple, binary, but this equation is the DNA of every neural network ever built. 6 years later, now in 1949, psychologist Donald Hebb published a theory with no computer behind it, just an observation. Neurons that fire together wire together. In formal terms, delta W equals eta times y. The weight between two neurons increases proportionally to both their activations. Hebbian learning. Unsupervised, biological, and still the intuition behind modern self-supervised learning. We now move to 1957, where Rosenblatt took the old model neuron and made it trainable. He called it the perceptron. Inputs come in, you compute a weighted sum, passes through a step function, and get a binary output. But there's a learning rule. If the output is wrong, we update the weights. Weight gets weight plus eta times the error times the output. The perceptron is drawing a line in space, a hyperplane separating two classes. Each mistake nudges that line, and Rosenblatt proved that if the data is linearly separable, this always converges towards more accuracy. In 1969 is the first real problem when Minsky and Paper, two researchers, published their book named Perceptrons, and they proved it. The perceptron just cannot solve the XOR problem. But what is XOR and why is it so important? Take 4 points. 0, 0 maps to 0, 0, 1 to 1, 1, 0 to 1, and 1, 1 to 0. If we plot them, we just cannot separate the ones from the zeros with a straight line. They are not linearly separable. And they proved that this model cannot do that, which would mean that it literally can't solve any problem, since in real life, no problem would really be that simple. So if it can't even solve the most simple nonlinear problem, which is XOR, it's basically useless. Research stopped, funding dried up, and the first AI winter started. Paul Verbos proposed the solution in his 1974 PhD thesis to train multiple layers by propagating error backwards using the chain rule, but nobody listened. In 1986, Rumelhart, Hinton, and Williams republished it in Nature. The idea is, we compute the loss at the output, then walk backward through the network. At each weight, the gradient of the loss equals the gradient of the activation output times the derivative of the activation times the input. That's the chain rule applied recursively. Every network training today is still using the same algorithm. Check out my last video about backpropagation if you want to understand the full mechanism deeply. We are now in 1989, where Jan LeCun, a computer scientist, took backpropagation and applied it to images. Here, the key insight was convolution. And instead of every neuron being linked to every single pixel, we slide the filter across the image. The output at one position is the sum of the element-wise product of the input patch and the filter. The same filter for the whole picture, which means they can share weights. This is known as translation invariance. This model could read handwritten digits at postal scale. Here's an example of it playing on the screen right now. However, at that point, computers were just not advanced enough to scale anything, and the second AI winter started. But after each fail is a breakthrough. Through the 90s, deep networks were too slow and unstable to train, but in 2006, Geoff Hinton showed that you could pre-train deep networks layer by layer. 4 years later, his student Alex Krzyzewski ran a deep convolutional network on 2 GPUs. AlexNet entered the ImageNet competition and got top 5 error from 26 to 15% in a single year. That gap was so large the entire field shifted overnight. We are now in 2017 when a team at Google published Attention is All You Need. They replaced recurrence with pure attention. For every token, you compute a query, a key, and a value. Attention weights are the softmax of the query dotted with all the keys divided by the square root of the embedding dimension. Apply those weights to these values and that's it. Stack it and scale it to hundreds of billions of parameters and you get every large language model that's running today. From a binary threshold to transformers, 8 years with 6 core ideas. The neuron, Hebbian learning, the perceptron, backpropagation, convolution, and finally, attention. That's the whole stack. Keep building.